Hello everyone, I hope you're doing well. So in this video, we're going to discuss Geeks for Geeks problem of the day, and today's problem is longest increasing subsequence, and it is a medium level problem. So this problem is again a very standard dynamic programming problem, and the problem statement is very simple. It asks us to find the longest strictly increasing subsequence from the given array. Right. So what do we mean by a longest strictly increasing subsequence? So first of all, subsequence is any set of elements from this particular array. You can take out any one of them and skip the rest of them. And the only thing is that the order should be maintained. And longest increasing means that the sequence should be strictly increasing. Right. So in this particular case, as you can see by the example itself, this is the whole array and this is the LIS that you will find in the array. So the first element is 0. Here we have 0, then we have 2 here, then we have 6 here, then we have 9, and then we have 13, and then we have 15. Right. So you see all of these elements are already in the same order in the original array, and all of these elements are strictly increasing in order. Right. And the size of this particular array is going to be 6. So 6 is our answer. And there will be no array which is longer than this particular size. So this is the longest increasing subsequence. Now we are first going to discuss the key idea behind this problem, which is not very intuitive at first, but it is not very difficult as well to understand. So the key idea is going to use n square time complexity, and the only reason we are discussing the key idea of this problem is because that particular idea can be used in other problems as well, and it will be very helpful to you there. Then we are going to look at an optimization over that idea which will help us to reduce the complexity of this particular problem to n log n. So let us quickly start with the problem. So till now, I believe you already know what is an LIS or a longest increasing subsequence. Right. So we have this particular problem statement with us. So first of all, let me just create an array. So if we have an array here, right. So let's say this is 0th index and this is first index, this is second, third, fourth, fifth and sixth, right? So this array is a very special array for me and I'm just going to call it my LIS array. So let's say initially I have an array of size 6, right? And I want to find the LIS of these 6 elements, right? So this is actually my DP array. I can also call it LIS. And the special part about this DP array is that let me first define what this DP array is going to store. So if I have DP of I, then DP of I is going to denote the smallest ending element possible for a subsequence of length I. Right. So this is our whole task. Now we have to find the value of this DP array, right? And once we find all of these values, let's say all of them were initially equals to infinity, right? So we initialize all the values with infinity. Now after finding all these values for the whole DP array, then the last index which is not equals to infinity will be our final answer, right? Because what we are doing is storing the smallest ending element possible for a subsequence of length I, right? So if it is possible to find an ending element for a subsequence of length 4, then definitely 4 is going to be my answer, right? Again, if it is possible for me to find an ending element for a subsequence of length 5, then 5 is also going to be my answer. But if I am not able to find an ending element for a subsequence of length 6, then obviously the last possible answer will be my final answer. So this is why the last element which has a non-infinity value will be our final answer after we have completed all the steps, right? So this is about the final answer. Now how do we actually find this particular value of DP of I, right? This is our main task now. So what we can just do is we can just traverse through all the values of A of I, right? So let's say we are at some ith position, right? So we have a for loop which is going to traverse through my array A, right? And once we have found, let's say we have A of I. Now for all the positions at which, let's say I have a loop J starting from 1 going till less than n plus 1, right? Why is it from 1 to less than n plus 1? Because this particular array J is going to traverse through my DP array or my LAS array, right? So this has my primary data student from index 1 to 6. So now for all of these values where LIS of J, let's say LIS of J is less than A of I. What that means? That there exists a subsequence of length J which is ending at a value let's say which is less than A of I, right? So if there is a subsequence of length J, what I can try to do is I can append this A of I after this subsequence, right? So it will become a subsequence of size J plus 1, right? So if this condition is true, what I can try to do is I can set LIS, let me just erase this, I can set LIS of J plus 1 is equals to minimum of LIS of J plus 1 comma A of I, right? So what I'm saying is, let me just repeat this part again. So I'm saying that if there exists a subsequence of length J for which the ending element is smaller than my current element A of I, then I can always append this A of I at the end of that particular subsequence of length J. Once I try to do this, then I can update my LIS of J plus 1 as minimum of LIS of J plus 1 as well as A of I, right? So I just take the minimum of both of those values because I want to maintain this property, right? That it should be the smallest ending element possible, right? So if I do this for all the elements again and again, I'll be able to form the LIS array or my required DP array, right? So the overall complexity, you can clearly see it is O of n square, right? And I'm saying it again that I have discussed this better only because this idea is very useful in some other problems as well. Now specifically coming on to this particular problem, there is a special property about this DP array or the LIS array that we are trying to form. You will observe that all of these elements are already arranged in strictly increasing order, right? Let's say we have this LIS array with us. So all of the elements, you will observe, what you can try to do is you can try to solve this question with brute force for smaller values and then try to print your LIS array, right? And you will always observe these values that you have in the LIS array will always be in some strictly increasing order, right? So if they are already in strictly increasing order, then you don't need to go on these elements one by one. What you can just do is you can just directly perform binary search on this and find the correct position of the current element, right? So let me just repeat this part again. For this particular problem, specifically for the longest increasing subsequence, you will realize that your DP array or your LIS array, whatever you can call it, is already in a strictly increasing fashion, right? So if it is already in some strictly increasing fashion, then you will realize that traversing through all the values to find the correct position of A of I is not very optimal, right? So to find the correct position, you can just directly apply binary search to the LIS array to find the correct position of the current element AI, right? So let's say this was the current state of the LIS array and now you encounter an element 5, right? So now you want to find the correct position of 5, right? How would you do this? If we go by the previous method, you would go to this particular first index, you will check that yes, it is smaller than 5, so I can try to form a sequence of length 2. You see that this is a subsequence of length 1, so you can try to form a subsequence of length 2 ending with 5. But now you see that there is already a subsequence of length 2 which is ending at 2. So it is not optimal to replace this 2 with 5, right? So this is cancelled. Now when we come on to the second index, we see that this is less than 5. So if a subsequence of length 2 is ending with 2, then I can try to form a subsequence of length 3, right? So for that I see that this 10 is greater than 5, so I can just replace this particular position. Now for all the remaining elements, since this is not less than 5, then I cannot do anything. Since this is not less than 5, I cannot do anything, right? So this is through the linear search. Now, how do we perform binary search on it? Using binary search, you just need to find the first position which is greater than or equals to 5. Right? Why? Let's see. So let's say this is not greater than or equals to 5. So it is not possible. This is not possible. And this is the first position which is greater than or equals to 5. Right? So I replace this particular position with 5. Right? So why this particular position only? Because this would be the first place at which there was an element greater than or equals to 5. So the key idea is very simple, that all of these elements are already smaller than my current element, so I cannot replace them. The only position I can replace is some element which is greater than or equals to my current element. So you must have got the idea why I am taking greater than my current element. But why am I also including the element equals to my current element? So let's say after all of this, I again encounter an element which is equals to 5. Right. Now with this LIS array, this is the first position which is greater than or equals to my current element. Right. If I only look for greater than, then my 5 will look at this particular position and it will try to replace 12 with 5, which is not the ideal case, because a subsequence of length 3 is already ending with 5. So I cannot have a subsequence of length 4 ending with 5 as well. If it happens, the subsequence would look something like this, that we have an element A, then we have an element B, then we have two 5s, right? So this is not what we want, right? We want a strictly increasing subsequence. So that is why we will also have to include the element 5 itself as well. So you have to find the first position which is greater than or equals to my current element. If you do this for all the elements and keep on replacing the values, then you will get your final LIS array. I'm repeating this again, that this property is only specific to this type of problem, that is longest increasing subsequence. But this key idea, this idea of n square approach that we have discussed, will work in many other problems as well. That is why it is very important to understand this particular idea first and then go on to the optimized version of the same problem. Right. So the optimized version is also nothing but just an implementation over this same idea that we already have here. Right. So the observation that we are making use of is that the LIS array is always going to be in strictly increasing order only. So instead of performing this linear search, we can apply binary search to it. Right. So I know that this concept or this problem of longest increasing subsequence might sound a bit tricky, but if you keep practicing these types of problems, then you would be able to understand it in a much better way. So now let us have a look at the final code and you will get an idea of how to solve this problem in login. So this is my code. What I've done is I created an LIS vector of size n+1. I've initialized all of the values with infinity. So in this case, it is going to be 10⁻⁹. You can take any element which is not going to occur in my input array. Right. So I'm initializing LIS of 0 with -1. So it is also a smaller element which is not going to be the part of my input array. Right. Now I'm just traversing through all the values and I'm just doing binary search. I'm using the inbuilt lower bound function in the LIS array and I'm looking for the value AFI. So this lower bound function will essentially do two things. If AFI is present in my LIS vector, then it is going to return me a pointer to the element which is equals to AFI. Right. But if AFI is not present, then it will return me a pointer to an element which is just greater than AFI. So if I get a pointer to get its index, I'm just going to subtract LIS.begin. Right. So if this position P is less than n+1, it means if this index exists in this LIS array, I'm going to update my LIS of P as AFI. Right. So you see, now I don't have to check that minimum condition, because this element that I'm getting will either be equals to my current element or it will be definitely greater than my current element. I've made sure by using binary search. Right. Now I can just run a reverse for loop, and for the first position where LIS of I is not equals to 10⁻⁹, that means it is not equals to infinity, I can just return the index I. Right. So this was all about today's problem of the day, and let me just quickly submit this and show you that this particular code works and the solution is absolutely correct. So you see, it passes all the test cases, and I hope that you guys were able to understand the solution. If you guys did, then consider dropping a like on this video, and don't forget to share thoughts in the comments, because your engagement with this particular video really helps the YouTube algorithm to understand that this video is actually helpful for you and you'll be able to reach more number of people like you who want to keep solving new problems. So I see a lot of people who watch these videos have not subscribed yet. In case you're one of them, then definitely consider subscribing. It's always free of cost, and you can always subscribe if you don't find the videos interesting later. So share this channel with your friends, and till the next video drops, keep coding, stay safe, bye bye.